Welcome to our latest chapter where we're talking about moving away from what we've been building up to in the past, which has been looking at means. Is one mean significantly different from another mean or a group of other means? Here we're getting away from our discussion of means and looking at mean differences, moving away from what t-tests and ANOVAs generally do, and now we're looking at what's known as a correlation, and we're taking two variables measured. In some ways you can think about it as a within subjects. You have to have for each person a measure on variable 1 and variable 2, and then we see if they co-relate, if those two things go together in a pattern. And of course, first of all, we have to decide, is it there? Is it really there? Does it really exist? That's the significance test. And then we have to decide, well, if we conclude that it is real, how large or important or what's the magnitude of it? And that's the issue of effect size. So probably there's nothing too conceptually different in terms of our hypothesis testing and what goes on afterward in terms of looking for effect sizes. But the process in which we get there and the way we're thinking about our variables is definitely a little bit different in terms of correlations. So here's a quick overview. We'll look at an important piece of information that we need to think about when thinking about a correlation is a scatter plot. What does it look like when we map these two variables against each other? What is the correlation coefficient? How do we calculate it? What are some barriers for interpreting it? And of course, then our hypothesis testing framework. So far, this is why we spend so much time thinking about different kinds of variables at the start of the semester, because typically with especially analysis of variance, but even t-tests as well, you got two means, and either you're in group A or group B, and that's a discrete IV, or for repeated measures, time 1, time 2, time 3. So discrete, you can only be in one category or the other. And then we've been looking at a continuous dependent variable. So does the grouping or the discrete variable show a pattern of differences on the continuous dependent variable? So for example, are there different stress levels for therapy 1 versus therapy 2? And of course, we have the classic example of a drug trial and comparing on some continuous dependent variable, is the difference caused by which drug you've been assigned. So now we're looking at the relationship between two continuous variables, and that's kind of the definition of a correlation. Correlation is a pretty robust framework. So there's some exceptions where we can even look at calculate a correlation with some discrete independent variables, but we're mostly going to be focused on relationships but with two continuous variables. We covered correlation in this chapter and then regression in another chapter, although in some other books I have used, correlation and regression are covered in the same chapter because they're so related. Basically, I like that we cover it separately because correlation gives us the background for thinking about these relationships between continuous variables. And I think with a formula that's pretty easy to understand what it's doing. And then regression, especially what we'll cover as multiple regression, allows us to move outside of the framework of just two variables. So conceptually, we're using correlation, but 3, 4, sometimes a dozen or more variables with regression. And of course, with that many variables, the equations get very complicated. So if we understand conceptually what the correlation is doing and how it ties to the formula, then even if we can't follow the formulas exactly with multiple regression, we still conceptually can imagine what's going on with some of the numbers in terms of the raw data. So first of all, let's talk about what's known as the scatter plot. I'm sure a lot of this is going to be some level of review for you, but just to make sure we're on the same page, I want to have covered all of the important background things to think about regarding correlations. So for example, here are two continuous variables. What is the time to complete an exam, and what is the score on the exam? And of course, they're both continuous. You have from 0 to usually 2 hours plus to complete an exam. And historically, one of my classes, I mean, there's some exceptions depending on especially online arrangements. And then of course, the score is a continuous variable too. What percent do you get, or what is your raw score of number of questions correct out of the total? So basically, We have two measurements of these continuous variables. And then we just want to see what does it look like when we graph them together, and that's the scatter plot. Now, it doesn't really matter which one we use for the x-axis or the y-axis. Typically, we think about the predictor variable on the x-axis, and if we're thinking there's a predictive power about knowing how long somebody took on the test, then we'll put that as our x-axis variable, and then what we think is being predicted, at least in part, which is your score on the test, that will be on our y-axis. And so we have, for each person, we have two data points, and as we see in the next slide, on a scatter plot, we can see where each person in the sample is. So for example, here is our continuation of the example from the previous slide, and so our, for example, exam time, our x variable is from 15 to around 65 versus the grades are 45 at the lowest to almost 100%. And we see here, as predicted, there's kind of a slight negative relationship, which means as we get higher on exam time, we see that the grades are a little bit lower. So the idea is that taking a longer on exam means maybe you just hadn't prepared and weren't ready, and you're taking the extra time thinking it might help, but it doesn't seem to be helping. You could also make the argument, if we were doing a hypothesis, that it could be the opposite. Well, people who just rush through it would do poorly, and if it was a positive correlation, low time would be correlated with low grades. High time, you're really taking your time, doing the best job you can with high grades. But of course, that's not what the data is showing us. It's showing us negative correlation. Low exam time, generally better grades. Higher exam time, better or generally lower grades. So now we need to move into what is the actual number that we get. And that's what we call the correlation coefficient. And it is the number summarizing a linear association. So sometimes we think there might be a curvilinear or nonlinear relationship between variables. And that's why we want to look at the scatter plot, because that'll show us. So for example, with the previous slide, you could imagine perhaps a curvilinear or U-shaped, either a regular U or an upside down U. Maybe it's that in terms of time to take the exam, there's a sweet spot on an average in the middle. So for example, if you take a really short time and blow through it, low scores. If you take a really long time, you just don't know the material that well. But if you take an average time, that's when you have the highest scores. So you have to look at the scatter plot in case there is not a clear linear relationship. But we do know that the correlation coefficient formula that we're going to use only calculates the linear association. So we look at the scatter plot, we determine whether it looks like it's a linear relationship, and then we can move forward and safely and confidently use the correlation coefficient formula. So a couple things to keep in mind. The correlation, the number, tells us first of all the direction of the relationship. Is it low and low to high and high, or is it high and low to low and high? Positive says low goes with low, high goes with high. Low variable x, low variable x, low variable y. Negative correlation is the opposite, high with low with high. So that means, for example, with coffee sales and temperature, the higher the temperature, the less people want hot drinks. The lower the temperature, the more they want hot drinks. So low temperature goes with high coffee sales, high temperature goes with low coffee sales. The correlation coefficient also presents to us the strength or the magnitude of the relationship. This is kind of nice because unlike perhaps an F ratio or a T statistic, clearly if we have a cutoff value of around 2 for a T statistic, and our T is a 7 or an 8 or a 10, we know our T is a lot bigger than our cutoff value. So yes, there's probably a big effect size there. But it's even more easy to see in terms of correlations, because if our correlation is close to 0, then we know it's not a strong relationship. The further it gets away from the middle, both in the -1 or +1 direction, that's the stronger the correlation. So it's a really intuitive instrument to use as far as compared to all the other statistics we cover in this class. So here's some examples of correlations, and we'll go over each of these in more detail. But clearly we're going to see a stronger positive means more clear pattern, more clustering toward this central line if we were to draw one that best represents the pattern. Weaker means it's clearly still looking like low to low, high to high, but there's just more spread outedness, more variability from that central line. Same thing with the negative correlations. And then finally 0. We don't know whether high goes with high or low goes with low, and that means there's probably either an exactly 0 correlation or something that's so close to 0 that it won't be statistically significant. So first of all, you can see the actual value here, a correlation of a positive 0.87. So the positive says low with low, high with high. And when you can clearly see in the scatter plot that it's obvious that there's a clear relationship, most of these dots are centered right close to what imaginary line we draw, very few outliers in the unusual areas, we see a very strong positive correlation. And keep in mind that a perfect correlation in positive terms is a +1. So this is already pretty close to perfection, even though it may not look like it from the first time we look at these. But once you start looking at more correlations and more scatter plots, especially if you collect some of your own data, you'll see that if you see a pattern like this, you know you got something that you can easily interpret. Now here we see a correlation of positive 0.47. So notice this is going to be, in many cases, again, if you just keep looking at more research or maybe are analyzing some of your own data moving forward, correlation of positive 0.47 is pretty good. It's going to be what we're going to describe as a medium correlation. A lot of social science, especially survey-based psychological research, you love to see correlations of 0.47. Sometimes you're just hoping for something like this with some of our weaker and more error-filled measurement methods. But you see clearly still low goes with low, high goes with high, but there's more bounce on average away from that central imaginary line that we could draw. Same logic for the negative correlation, except now notice the magnitude or the strength of the relationship is exactly the same as our positive 0.87 correlation, but now even though the strength is the same, the interpretation of the way the variables relate to each other is exactly opposite. Instead of low with low, high with high, as in a positive correlation, here we have low on our x variable goes with high on our y variable. And by extension, high on our x variable goes with low on our y variable. And then finally, in terms of correlations that are non-zero, we see again the same magnitude of a 0.47, but instead of a positive 0.47 as before, now it's a negative 0.47. And once again, instead of with a positive, low going with low, high going with high, here it's just low x going with high y and high x going with low y because the correlation is negative. And finally, we see here, this is what a correlation of 0 generally looks like. Again, there's no clear pattern. I'd have very little confidence in drawing a line in terms of which way it would tilt, whether upwards or down. And so even if this, rarely will you get a correlation that's actually 0. Just like with a t-test, you'll rarely get a mean difference that's no difference. The means are exactly the same, but they're so small that there's much more standard error that overwhelms any sort of meaningful interpretation of the variables or the relationship. So a couple things to think about. Again, we're talking about linear relationships. So again, going back to the last slides we covered, those scatter plots are clear linear relationships. Imagine what those dots would look like if they formed instead of a line, either upside down U or a regular U or even a W. The less it gets away from linear, the less appropriate it is to interpret the linear correlation formula. Now we have some symbols as well. So first of all, classic R. This is what we're often dealing with in research. Again, this is data from our sample correlation coefficient that we calculate. But when we're thinking about our hypotheses, we're talking about the population variables or values because we're doing our inferential statistics, not just because we care about that sample, but because we want to make reasonable assumptions about how well that sample represents the larger population. And so the population correlation symbol is known as rho. So here we think about the correlation as essentially being another ratio. So basically, our total variability of our x and y, and how much of that total variability can we pull out and say is due to variability that goes together, or covariance, shared variance between x and y. So as kind of mentioned before, but made official here, R can range from -1 to +1. There's two ways to have a perfect correlation, either +1 or -1, and a correlation of 0 equals 0 relationship. So once again, if we think a correlation of 0 means there's all this variability of x and y, but none of it's shared, 0 on the numerator versus whatever total variability there is. On the other hand, if it's a perfect positive relationship, think about total variability and going together, for example, explains all of that total variability. So for one example would be like conversions from height in inches to height in centimeters, right? It's a perfect ratio. So we can have a whole bunch of people's heights in inches and we convert them into heights in centimeters and then we correlate them, and no surprise, it's a perfect positive. Any differences in those variables are perfectly matched by the differences in the other variable, inches to centimeters. And of course, in real life, we don't hardly ever get meaningful, perfect correlations. And another thing to always consider, you've probably seen this half a dozen times already, is that correlations can never be greater than 1 or less than 1. It's baked into the formula, and so if you're ever doing one by hand, that means something went wrong. And chances are, if you're using statistical analysis software, something really went wrong, something maybe impossible happened if you get output that says a correlation outside of this range. A couple things to keep in mind. Size of correlations, the closer to 0 we get. 0.1 is small, 0.2 is small. Once we get to 0.3, this is a moderate correlation. I think I had that wrong when I said that earlier, that a 0.5, I was thinking that 0.47 in those sample scatter plots was a medium correlation. 0.5 is large for sure. So, once you get to 0.3, that means there probably really is something there. And 0.1, again, just because it's small doesn't mean it's not useful. It just means that it's only explains part of the variability in terms of how those variables are related, which also means if you see that there's a correlation of 0.1 between two variables, thinking ahead to regression and multiple regression, maybe there's some other variables that we can sort of add on that are correlated to other unique parts of our dependent variable. And even though we have small prediction of one variable, if we add a couple more, we can get to maybe total explanation of 0.2 or 3. It just takes us, instead of one variable, maybe 2 or 3 or 4 to do that. So let's look at some of the numbers here. Basically, the Pearson, sometimes called the product moment correlation, this generally assumes that both variables are continuous. And there's a number of subtypes of correlations meant to deal with different kinds of variables, such as categorical or nominal, discrete variables. So you can still calculate correlations with discrete variables, but you might have to do it by hand if your statistical analysis software doesn't have that button to click on. And just know that the default when you calculate a correlation is the Pearson linear relationship between two continuous variables. So also remember, here's our concept. the covariance between two variables relative to the total variability of the two variables. What's our formula for this? Well, we have a new concept here, which is SP. We're going to find out that means the sum of products. But below, remember when we think about calculating indices of variability, back to our first exam material, sum of squares, right? So going back to simple sum of squares for variable x, sum of squares for variable y, and then we just have to see what is this SP relative to our total variability on the bottom. So basically, here's what our SP looks like. It's basically just saying that we are taking our x values minus our mean of x, so deviation score for x. Going back again to exam 1 material, except now we're doing it twice because we have two variables, and y minus the mean of y. So we just have our deviation scores for our x variables and our y variables. And we can use those to calculate the sum of squares for our denominator, and we will. But we have this extra column here, the sum of the products, where we take our deviation scores from our x times our y, and that gives us our products. The products of the deviation scores of the two variables, we add them up, and that gives us the sum of those products. And that's simply the numerator for our correlation. Now, there's also what's known as a computational formula, not necessarily going to be super important for our purposes in this class. But if you don't want to have to do the whole table, you can also sometimes maybe given one of these components and just pop these values, x times y, add those up, and then sigma x over n. So there's times if you're not given the sum of products, you could probably calculate it, but you can also use an alternative way to get there. So we have our sum of squares, and then we have kind of like to get to our sum of squares, for example, if we break it down, and this is again just thinking about the process of calculating a standard deviation from exam 1 stuff. Basically, x minus the mean of x deviation score, if you just add all those up, you get 0. You add up deviation scores, mathematical fact that you get 0. But to get a meaningful index out of it, you have to square it, right? And you break that down, and that looks like x minus the mean of x deviation score times that deviation score, squared, essentially. The products looks very similar to that. It gives us kind of a sum of squares metric, except instead of squaring our deviation score for one variable, we just multiply the deviation score of x and the deviation score of y for each person in our sample. So important note, unlike the sum of squares, anytime you square something, the result is going to be positive. But the sum of products can be negative. So if you're ever calculating this by hand, you have to be careful to make sure that you are including the negatives and being precise with them. And that makes sense. For example, if this mean is higher than the raw value, x minus a higher mean gives us a negative value. But y minus a smaller mean can be a positive value. So if we have a negative deviation times a positive deviation, we get a negative score. That's part of the things that are added up to get to our sum of products. So going back to our Pearson correlation formula, basically we are comparing the covariance or the relationship of x and y with the total variability. And if you think about that in relation to the F ratio for ANOVA, you know, we have our mean squares within and mean squares between. Which one goes in the numerator? It's the mean squares between, the differences between groups relative to the total differences in all the scores together. Again, this is not necessarily for exam purposes, but just one of those kind of cool mathematical proofs that if you just want to take it for truth today, you can. If you really want to think about it, you can do a deeper dive. But basically, we can use standardized or z-scores as well, and using those z's, you can pop those into a correlation to calculate directly to R without even having to bother with that sum of products step. So a couple things to keep in mind. We've done the work, we've calculated our correlation, we've looked to see that our scatter plot looks like it is linear, so we can use our linear formula. First of all, correlation does not equal causality. It means it could be that one variable causes the other. It could be that something else causes both of them. It could be that they're related, but not in a meaningful way if we think about it conceptually. It's a good first step if we want to think about causation, and maybe that leads us into designing an experiment to test causation in a more strong way later on. But by itself, we don't want to overinterpret the correlation. Also, the correlation is greatly influenced by the variability of the data. Typically, more variability is a good thing. And of course, little variability, everybody is the same on both the variables. There's not that much to predict if everybody's the same. Also, R is greatly influenced by extreme data points, which means if we have a positive correlation where low goes with low, but you have a couple data points where low goes with high and they're really sticking out relative to the other dots, that's really going to affect the calculation or the result of the correlation that we get. So more on each of these to come. So here's the idea about correlation and causation. It depends. We can have a theory about which comes first and is doing the causing and which is doing we're being affected. But really, that's just how we're lining it up on our scatter plot. But we can switch the variables on the scatter plot. We can change our y variable to our x variable, switch those out, and the correlation stays the same. It's just to help us in thinking about if there's an order or a clear, at least as we predict, predictor-outcome relationship. But of course, we can only consider two variables at one time with correlation, and it could be that some other factor causes both. So for example, if we think about variables, we could see a positive correlation between nutrition and IQ among school children. So if you eat healthier, you have a higher IQ. Well, okay, is that all of the story? Well, basically, we don't know if we're going back to our options here. It could be that smarter kids choose to eat more nutritious food, or it could be that nutritious food in some way affects better looking IQ. Or it could be that a third variable, such as the annual income of your house, socioeconomic status, could be causing both. Essentially, if you have enough money to pay for good nutrition and good educational experiences that foster IQ, I won't say causes it, because you can have a lot of genetic potential for IQ that's there whether the person's in a rich house or not, but it might not be able to be expressed unless you have the socioeconomic status to be able to allow for that IQ to be fostered. So again, could just be the two variables. We don't know just from the correlation only which way the causation goes. And we don't know, since we haven't measured them, the effect or account of this relationship that additional variables could account for or explain. We also have what's known as range restriction. And basically, when you are taking a sample, and this goes back to the difference between samples and populations leading to sampling error, this is just a predictable type of sampling error. Basically, when the data are limited, especially so smaller sample sizes, we're going to see what's known as range restriction. And if we're thinking about our two variables, let's say we want to see if GRE is related to, this is graduate record exam, a test you might have to take to get into a certain graduate program you're looking into. If you're looking at the relationship between GRE score and graduate GPA, there's one problem here. You don't actually get the GPA of people who took the GRE but were not admitted to grad school. So the range restriction is the only sample you have data for both variables, graduate record exam score and graduate GPA, are the sample that got admitted. So we never have the data for the sample that didn't get admitted, and that means that whatever correlation we get has been range restricted, and the outcome of that is probably that our correlation is going to be lower or look worse than if we had the data for everybody who took the graduate record examination, and if they were all admitted to grad school and we could calculate a GPA for them. And so, of course, sometimes we can't do that, unfortunately. We just have to think about our samples and if there's potential range restriction, and then factor that into our analysis. So specifically for this example, we know it's a range restricted sample because we only get data points on both variables for people who have been admitted to grad school, and we still find a correlation of 0.3. What would happen if theoretically we had the entire range of values for the entire sample? Good and bad GRE scores and the GPA that goes with them. Chances are if we had that data, our correlation would look even better. Now, that doesn't mean we can say, we can just pretend that our correlation is higher than we actually got, but if we're explaining it in our write-up, we can account for the fact that there's likely range restriction, and this is our estimate, but considering that issue, we would guess that the actual correlation between these two variables is higher if somebody wants to go out there and get that data. So continuing our discussion of range restriction, again, we don't have values, and they can't factor into the correlation if we don't have values on both variables. And so the range restricted sample is probably, it doesn't matter in terms of making it useful. So we don't say, well, we know there's range restriction, so our correlation is junk. We just have to acknowledge that's a potential limit in our interpreting our correlation. And again, when there's range restriction, we will underestimate the real association between the two variables. So for example, if we think about this pictorially, we see our GRE math scores, the full range, and then we see the cutoff of, this is probably a pretty selective grad school, but they only selected people who have GRE math scores higher than 750, right? So these are the people we have who got into grad school, and then we can later on get their GPA and run the correlation. But we have to think theoretically, what about these other people? It probably does look something like this, but what happens if we get this correlation and there's really no association? That's where things get really confusing. We didn't get a correlation, but we think there's strong range restriction, so there might be a correlation in the population, but what we got, we don't have much to go on in terms of conclusions, potentially about how strongly GRE math predicts graduate school performance if the range restricted sample doesn't give us a clear correlation. We also have to think about the outliers. So keep in mind that an outlier can be higher or lower than average on either variable. What's even more problematic is when there's a data point that's an outlier on both values. So for example, think about if we have a positive correlation, low going with low, high going with high, we can have somebody who has a much higher X score than the other one, than the other people in the sample, but if their Y is also high, it doesn't hurt that much. but if they're extreme outlier on the x and the y, so they have a high, super high x and their y corresponds with a low value, everybody's going high with high, and this x and y is high and low, that's really going to cut down our correlation that we calculate. So it's important to think about this, and we'll have a couple images to talk about this, but we have to think about looking at the scatter plot and thinking about if the outlier is going to make our correlation artificially bigger than it is, or it could make our correlation artificially smaller. It depends, again, on the pattern of the outliers. So, for example, we see these 5 scores. Generally, you can see it's also range restricted because we don't, out of our full range of x and our full range of y, we're on the low values of both of those variables. So really kind of questionable data here, low correlation. What if we have someone who's a super high outlier on both the x and the y, but it sticks with the general pattern of a positive correlation? Well, look at what the correlation does. Maybe negative, but now it's almost getting close to perfect here. We know that this is far from perfect without this outlier one. And of course, what would happen if this outlier were then moved to this range or this range here? Well, instead of being a positive correlation, we can see the impact that this had on changing essentially a 0 correlation into super positive. If that dot was moved to either here or here, well, we'd probably see a pretty clear negative correlation if that were the case. Again, in this range, low on the y with high on the x, negative correlation, low on the x, high on the y, whereas clearly this one is high on the x, high on the y, and so it's so much of an outlier that it basically drives the entire correlation. Here's why we need to have large sample sizes for the most part, because if we have big sample sizes, the effect of any one individual outlier is going to be less. Still, we have to account for the greater than average effect that outliers have, but with big sample sizes, we worry about the effect of one individual outlier less. We also have the idea of correlation with R squared, sometimes called big R squared. Basically, R squared measures the proportion of variability in the data that is explained by the relationship, essentially meaning that what is the variance accounted for? Sometimes called the coefficient of determination. I won't use that for our purposes, but you may see that elsewhere. And essentially, we know these two variables are related. What is the variability in one variable that the other variable accounts for, explains? And so in this case, if we have very strong correlation of R of 0.8, take that and square it for R squared, our effect size, and we see that 64% of the variance in variable y is explained by variable x. And notice that goes both ways. It's also that 64% of the variability in y is explained by x, as the variability in x is explained by y. So let's quick run through how hypothesis testing works with correlations. Basically, does a correlation exist, significant or not? And of course, we have our notation and our symbols here for our population and our sample values. And basically, in a non-directional hypothesis, we essentially say the null is in the population, there is no correlation. Alternative says that there is a correlation in the population. So again, it doesn't have to be exactly 0, but close enough to 0 relative to the error that we can't determine there's a significant relationship present. So we just have to calculate our correlation. We get our sums of squares x, sums of squares y, and our sum of products. And we also have a table in the book. This doesn't correspond to in our current book, but correlation tables back there with the others. And of course, what do we need in terms of calculating or finding a critical value? Basically, we need our n size. And the nice thing is n, what's our degrees of freedom? Well, we have a correlation, two variables, so degrees of freedom is going to be n minus 2. We have our alpha level, and then again, our degrees of freedom is pretty simple to calculate. It's always n minus 2 because we have two variables, and for each variable that we're including, we're losing a degree of freedom. And if the absolute value of the sample R is greater than our cutoff, then we reject the null. We say there is a significant correlation. So in terms of an example of hypothesis testing, let's say we have an n size of 30. We choose a two-tailed test. Now, of course, if we want to do a one-tailed test, we can predict or hypothesize that there's going to be a positive correlation or a negative correlation. But unless we're pretty sure and want that extra power and can justify, we're probably going to go with the default two-tailed test. And we see degrees of freedom of 28, and the calculated correlation coefficient is 0.3. So we got a medium correlation there. What is our hypotheses? What's the critical region? If you look it up in the table, here we see a value of 0.36, and we need our correlation 0.3 to be greater than 0.36. So that means we cannot reject the null. We fail to reject, and we say we have not detected a significant relationship. And you might be thinking, well, if R of 0.3 is a medium correlation, shouldn't it be significant? Well, we look at the sample size, and probably our correlation is close to the cutoff value. What would happen if we had a sample size of twice this? Our cutoff value would be smaller, and our correlation of 0.3 would almost certainly be significant in that case. So, part of this is due to sample size, and rarely, in terms of publication standards, are you going to see a result or a sample size based on 30 people being able to be published. We just need to see a bigger sample size so we can be more sure regarding the conclusions of the significance test. And then finally, here's what things look like in terms of APA style. Basically saying our alpha level, the chance that we made a type 1 error, a 5% chance. But the correlation says that education and annual income were significantly related, and we know since it's positive, we know that the more education or higher level of education you had relates to higher income, lower education to lower income. And also, it would be appropriate right after the R in parentheses to include the degrees of freedom used for the test. So we could even do better than what I've just presented here. In terms of info, you might want to think about the conclusion of the analysis. So anyway, we've got to the end of correlations. Hopefully this is fairly intuitive. And the most important point, I think, is once you've got this down, we can jump right into the land of regression, which unlocks a lot of additional things we can do that are just not possible if we're only looking at correlation. So more to come now that we've become familiar with this framework.